Just any question before we continue? Now let us look at one coincidence. That is, at this level we will just think that it's a coincidence. Now we had calculated the velocity of the center of mass as a function of time. It is mu k times g times t. We also calculated the angular velocity as a function of time. This is the magnitude. So let's look at this combination. I center of mass omega plus mr v center of mass. We know that omega is a function of time. The velocity of the center of mass is a function of time. So let's look at this one. This is I center of mass times omega I minus mg mu k r over I center of mass times t plus m times r times mu k g times t. Well, let's see here, if we just multiply this term with this term, we get mg mu k r times t, which is mg mu k r times t. This is a minus sign, this was a plus sign, so they will cancel each other. So this term cancel this one. So I center of mass omega at the time t plus mr v center of mass at the time t is equal to I center of mass. Well, omega I is nothing but omega at the time t is equal to 0 plus mr v center of mass at the time t is equal to 0. Well, this term is just 0. The initial velocity of the center of mass is just 0. We just released it from rest. So we see this expression, this is I center of mass times omega plus mr v center of mass. We evaluate it at the time t is equal to 0, we get some value. We evaluate it at some later time t, we get some value. And this expression tells us that that value is the same. So here we have an expression that doesn't change during the motion of our system. So I center of mass times omega plus r times m v center of mass. This is constant. Just like we had the conservation of energy. I mean, if you remember when we were discussing the conservation of energy, we said that energy is conserved, so if you evaluate it at any 2 times during the motion of the object, the value you obtain will be the same. The energy will be constant. So here we have another conservation law. So this is a conservation law. Now, of course, we show this conservation law only for the example of the yo-yo, but now we will prove that this is, in fact, a general conservation law. Now, you see here, in this conservation law, here we have some expression like mass times the velocity, which we know is the momentum. And this conserved quantity, we will call it the linear momentum. No, angular momentum, sorry. Now we will describe the angular momentum. At least in the, we will call this combination the angular momentum. But now, let's start with the more general treatment of the angular momentum. Because you see here, I have mg mu k rt with a minus sign. Here I have mg mu k rt with a plus sign. So these two terms, they just cancel each other. They're exactly equal. So there is no time dependence left in my expression. And this combination is time independent. Although omega is time dependent, the velocity of the center of mass is time dependent. Each one of these terms are time dependent. The combination is time independent, which tells me that that combination is a conserved quantity. Now first, let's start with the simplest case we can imagine. Let's just imagine a point mass. Now if you remember, we also started discussing the angular velocity, the dynamical equations for rotation from a point mass, because we already know how the point mass behaves. So we have this point mass, there is this force acting on it. It rotates around this axis, let's call this vector the r. So we already said that from this system, what was the tangential acceleration of my point mass? Let's call this angle theta. F sine theta over m. This is just Newton's second law. The component of f in the tangential direction is f sine theta. So if I divide by m, then I obtain the tangential acceleration of the system. Of course, there will be also some radial acceleration, which for the time being, we do not really care about its value. And from this expression, if you remember what we said, that we knew that alpha was equal to tangential acceleration over r. And we put it over here so that we determine that alpha is equal to f sine theta over m times r, or then we said that mr squared alpha is equal to f sine theta times r, or in vectorial form we said that I times alpha is equal to r cross f. This is what we can derive. Now let's look at alpha a bit more. Or rather than this, let's look at this combination, r cross f. This is equal to r cross f plus t. Do you agree? You see, if I just redraw my system, this is my mass, this is the f, this is r. So there's a tension on this string. Well, you see, what is r cross t? R cross t is just 0 because r is in this direction, t is in the opposite direction. The angle between the two is 180 degrees, so the cross product is 0. This is equal to r cross f total, the total force acting on my system. This is equal to r cross. Well, now Newton's second law, we know that Newton's second law tells me that the total force acting on a system is nothing but the rate of change of the momentum of that particle or of that system. This is equal to r cross p minus dr by dt cross p. Now here what I did was, I just used the chain rule, not the chain rule, but the derivative of the products. If you take the derivative of a product, then that derivative is the derivative of the first one times the second one, which I subtract, plus the first one times the derivative of the second one, which is the term that I have over here. I just use, okay, this is the total force. I use Newton's second law. I'm just using the derivative of the products. But now this dr by dt is nothing but the velocity of my object. And p is the momentum of my object. If the velocity of my object is in this direction, then the momentum of my object is also in the same direction. Agreed? So this is the velocity, this is the momentum. They are in the same direction, these two vectors. So the angle between the two is 0 degrees. So that cross product is 0. Well, you see, if you take the derivative of this term, you get the derivative of the second one multiplied with the first one, the term I want, plus, as you said, the derivative of the first term times the second one, but that term I don't have on the other side. So I have to subtract it. So this term over here is equal to this one. Or let me write it explicitly. R cross P is equal to dr by dt cross P, as you said, plus R cross dp by dt. But on the left-hand side, I have this one, R cross dp by dt, this term only. So this term is equal to this derivative minus this term, this one. But that term is 0 anyway. Because I have these two vectors, they are pointing exactly in the same direction. So the angle between the two is 0. So I'm left with this one. The torque of an object acting on an object. Remember, I started with the torque. This is R cross F. This is equal to d by dt R cross P. This is what we had derived. Now compare with Newton's law. F is equal to dp by dt. And we always said that in rotational motion, the role of F is played by the torque. Torque is similar to the force. Torque in rotational motion is similar to the force in linear motion. And this quantity over here is what we define as the angular momentum. Just similar to the linear momentum, this is angular momentum. In this case, it is for a point object. Now, of course, since there is this R over here, you can define this angular momentum relative to any origin that you like. This is just a point object, although we started by discussing this object rotating around some fixed point. I mean, for any object, you can define this quantity, this angular momentum R cross P, even if it's just doing some linear motion. And so, of course, the value of the angular momentum will depend on your origin. So you choose your origin once. If you change your origin, you will get a different angular momentum. But you first have to fix your origin once. You choose your coordinate axis, you fix your origin, and in that case, there's a given angular momentum. Now, any questions on this one? for the time being, this is just a definition. Just like when we're defining the momentum as mass times the velocity, now we are defining the angular momentum as r cross p. Up to this point, it's just a definition, but now we will see that it turns out to be useful. We will be able to make use of this definition. Now, any questions on this one? Now let's look at the angular momentum of a system of particles. Remember, we are studying rigid body rotation, angular momentum. Of a rigid object. You see, we have, let's just imagine this rigid object, and it can be rolling and translating at the same time. Let's just say that it is rotating around this axis. That axis has some velocity v. And there is also a rotation. Let's say that it's rotating. It has an angular velocity omega. This is our coordinate axis. We have some inertial reference frame. You see, one point of confusion seems to be when we are choosing this rotation axis in our object, we are not changing our reference frame. Our reference frame is always fixed. We just choose an inertial reference frame, and our reference frame is that one. We are writing everything with respect to that reference frame. Now, of course, to describe the motion, we choose some coordinate axis and describe it as rotations around that coordinate axis. Now, if you would go move with that coordinate axis, this rotation axis, then in that reference frame need not be inertial. But that is not what we are doing. We are always in this inertial reference frame. Now, I already know the definition of the angular momentum for a point object, r cross p. So I chose my origin is over here. This is my coordinate axis in my inertial reference frame. Now, if I want to calculate the total angular momentum of this object, I have to calculate, let's say, just take this very small mass over here, mi. It is rotating it's rotating around this axis, so it has a velocity due to that rotation. Let's say vi, it is moving with, let's say vi is equal to v, because the axis is being translated. At the same time, this point is moving relative to my axis. Plus omega cross ri. This is the velocity of the rotation axis. This is the velocity of this point relative to my rotation axis. Now this ri is the position of this point relative to the rotation axis. And this is the velocity of that point in my inertial reference frame. Everything is in the inertial reference frame. Now, any questions up to here? Omega is the angular velocity of the rigid body. We had already seen that the angular velocity doesn't depend on the choice of the rotation axis. Angular velocity is always the same for every rotation axis we choose. Because if it makes one full turn with respect to one rotation axis, well, it makes one full turn relative to any rotation axis. So angular velocity doesn't depend on your choice of the chord rotation axis. This omega, you just look at the, it's the you are in your inertial reference frame, you are looking at it and just measuring how long it takes to make one full rotation. It is this omega. Well, then we can write the angular momentum of the system. This is just mi r cross vi, or ri, sorry. Okay. Let me just change a bit the notation. This, let me call it di, and ri is the position relative to this object. This is my r. ri is r plus di. I'm writing the angular momentum relative to this point, relative to the origin of my reference frame. Then the position of this very small mass is nothing but this position of the rotation axis plus the position of this very small mass relative to the rotation axis. This is equal to mi r plus di cross product v plus omega cross di. Okay, this is the total angular momentum. Of course, we will simplify it a bit. Now, any questions up to here? This is the position of that very small mass, mi, relative to my origin. This is the velocity of my object of that very small mass in my inertial reference frame. And here this v, this large v, is the velocity of my rotation axis. Omega is the angular velocity, and vi is the distance of this mass mi, is the position of mass mi relative to the rotation axis. Okay, now let's just multiply them up. I have mi r cross v plus mi r cross omega cross di plus mi di cross v plus mi di cross omega cross di. Okay, I have all these terms. Now let's try to make sense out of them. The first one. Well, this r is just the position of my axis. It doesn't depend on which point mass I'm considering on my object. V is the velocity of my axis. Again, it is independent of this summation. So I can just take them out of this summation sign. So the sum over mi just gives me the total mass of my system. This is equal to r cross m times v. Well, if my axis went through the center of mass, then I could identify this with the momentum of the center of mass. But remember, my axis doesn't necessarily go through the center of mass yet. So this is not necessarily the total momentum of my system. Plus, well, again, if you look at over here, r is independent of the summation, omega is independent of the summation. So there I can just take them out, r cross omega cross mi times di. Well, there's this weird term. But again, if you look at this one, mi di, it looks like the position of the center of mass. In fact, it is the position of the center of mass relative to my rotation axis. Now, if my axis went through the center of mass, then again this would have been 0. It would be the 0 vector because the position of my center of mass would be 0 relative to my rotation axis if my rotation axis passes through the center of mass. Let's look at this one. Mi di cross V. Again, I get the same combination, the sum of Mi times di. If my axis went through the center of mass, again, these two terms, this term would also be 0, just like this term. And finally, Mi di cross omega cross di. So this is the most general form. Now if you look at this last term, omega cross di is the velocity of my object relative to the rotation axis. So m times that velocity we can identify as the momentum of my object relative to the rotation axis. di is the position relative to my rotation axis. So this combination over here is nothing but the angular momentum relative to the rotation axis. This term, well, for the time being, this looks like a momentum. So this is, in a sense, just like the momentum of the rotation axis relative to the origin of my reference frame. This term looks like the momentum of the rotation around the rotation axis. Well, these two terms, I don't have any interpretation for them, but we can get rid of them by just choosing an axis that goes through the center of mass. And that is what we will do. Now, if you choose an axis that goes through the center of mass, then this would be 0. And hence the total angular momentum of my object, and V would be nothing but the velocity of the center of mass. So L will be our center of mass cross P center of mass plus Mi di cross omega cross di. So basically, for example, when we were discussing the kinetic energy, we said that if you have an object that is both translating and rotating, you can split the motion into two, the kinetic energy into two. We could say that, okay, there is one, the kinetic energy due to the translational motion of the center of mass, plus there is a kinetic energy due to the rotational motion around an axis passing through the center of mass. So if we choose the axis to go through the center of mass, then we had this separation. The same thing holds for the angular momentum. So here we say that the angular momentum of an object relative to some point, if you choose to describe its rotational motion as a rotation around an axis going through the center of mass, is again the angular momentum of the motion of the center of mass as a whole, as if it was a point object, plus the angular momentum due to the rotations around an axis going through the center of mass. So again, we have this separation between the two. Here, because you see, I have a di over here, another di over here is squared. And mi times distance squared, does it ring any bells? Yeah, we will express this in terms of the moment of inertia. Now, the important thing is that if you choose an axis that goes through the center of mass, you can split the angular momentum into the angular momentum due to the translational motion of the center of mass plus the angular momentum for rotations around the center of mass. Now, if you see, if omega is 0, if there is no rotational motion, still there is an angular momentum due to the translational motion.
Is it because of the same concept that when you rotate?
Exactly. If you remember the example that your friend reminded us, if I'm moving in a straight line, I am still rotating relative to him, for example, because when he looks at me, he has to rotate his head. The orientation that he observes me, the direction that he observes me, my direction is constantly changing. Of course, if I'm moving straight towards him, in that case, I'm not rotating relative to him, but I'm rotating relative to her. Just like that, if you are rotating, you will get an angular momentum. If I'm moving in this direction, well, I have a linear momentum in that direction. Relative to him, my position is in this direction. So R cross P, the angle between the two is 180. So I don't have any angular momentum relative to that point. But relative to that origin, the origin at her point, I have an angular momentum. This is R, this is P. What is the direction of my angular momentum? If I'm moving straight, I'm moving straight. What is the direction of my angular momentum? R cross P. What's the direction of this rotation? Right hand rule, R cross P is in the upward direction. So I have an angular momentum in the upward direction. Well, let's see. Let's, just for the sake of simplicity, let's assume that the axis going through the center of mass is fixed. Okay. So if the axis going through the center of mass is fixed, this is 0. This is not 0. I still have some angular momentum. So that is why I'm saying that this is the angular momentum of the object due to its rotation around the axis passing through the center of mass. Now we will calculate this weird looking expression. Now we have this object. Let's say this is the center of mass. It is rotating around that axis, around an axis passing through the center of mass. And let's say that center of mass is at rest, is equal to 0. So L will be nothing but mi di cross omega cross di, but you can also just write it as mi di cross vi. This and this, they are just the same. Now, let's look at this point. What is let's just assume that this is the direction of omega. What is the direction of the velocity of this object, of that point? Right hand rule is just rotating like this in a counterclockwise sense. So this will be in this direction. This is my Ri. So let's just, what is the direction of R cross V? Or not Ri, di. What is the direction of D cross V? So So this is D, this is V, D cross V. Just imagine your right hand. So it is in fact, D cross V is in the same direction as omega. So we can say that this is equal to Mi. So let's write what's the magnitude of that object. D cross V, what is its magnitude? It's Vi times Di. What's the angle between the two? They are always 90 degrees. Sine of 90 degrees is just 1. We just said that it is in the same direction as omega, so let's just put an omega hat over there. It's the omega vector, the unit vector pointing in the direction of omega. What is Vi in terms of omega and Di? What's the speed in terms of the angular velocity and the distance from the rotation axis? It's the product. So Mi times omega times Di in the omega hat direction. This is equal to Mi Di squared times omega in the omega hat direction. Well, this is nothing but the angular velocity, the moment of inertia. And this is nothing but the angular velocity vector. Again, if you compare to the one-dimensional case, you see, in the one-dimensional case, linear momentum was mass times the velocity. In the rotational case, instead of linear momentum, we have angular momentum. Instead of mass, we have the moment of inertia. Instead of angular velocity, instead of linear velocity, we have the angular velocity. So this is the angular velocity due to pure rotations. Well, this is valid. Although this expression that we use over here, you can say that as long as it doesn't even have to be the center of mass. As long as my rotation axis is at rest, L will be always equal to I times omega. I is the moment of inertia relative to the axis. Now this is true even if the axis doesn't go through the center of mass. Here the only thing we assume in all of this derivation, in fact, is that the object should be, the rotation axis is fixed. But even if it is not fixed, in the general case, the angular momentum will always be either I times omega, if axis fixed, or center of mass cross P, center of mass, plus L center of mass, or I center of mass times omega, if axis goes through the center of mass. Now, if you prefer to write the angular momentum as the translation of some arbitrary axis plus rotations around an arbitrary axis, in that case the expression gets much more complicated. So these are the two cases in which the expression for the angular momentum simplifies. Either you have to have a fixed axis or you have to choose an axis that goes through the center of mass. Now, any questions? up to this spot. Well, you see, the nice thing about this axis passing through the center of mass is that as long as you consider the torque relative to an axis, relative to the center of mass, and the angular velocity, or you describe the motion, the rotation relative to an axis passing through the center of mass, you can use exactly the same results. Nothing changes. If you want to use an arbitrary axis not passing through the center of mass, then don't do it. Your life gets really complicated. But if you choose an axis passing through the center of mass, whether the object is doing some rotational, some projectile motion, etc., nothing changes. You can use the same thing. So when you're choosing an axis, you should choose either an axis that is fixed or an axis passing through the center of mass. In the case of the projectile motion, you cannot choose an axis that is fixed. So the only option left is you should choose an axis passing through the center of mass. Other questions? So let's do an example. I have a rigid rod with massless rod with two masses attached to both ends. Let's say this is my omega. So you can imagine that I have this rod with masses attached, so it's making such a motion with masses at both ends. Let's calculate the direction of the angular momentum. So what is the direction of the velocity of this mass, of the top mass? Into the screen, out of the screen. So you see it is rotating like this. So it is into the screen at this orientation. Its velocity is into the screen, so its momentum is into the screen. What is the direction of the angular momentum? Well, this is R. So let me see. This is R, this is P. They are at 90 degrees with each other. This is R. This is P. R cross P is in this direction. It is towards the axis. So this is the angular momentum of the top mass. Now let's look at the other one, this one. What is the direction of its momentum? It's towards you. So remember it's rotating like this. So it's going out. So the direction of angular momentum, okay, this is R, this is P. R cross P, let's imagine this rotation. With your right hand, this is the direction of R cross P. It's in the same direction. So the total angular momentum is not parallel to omega. Then L, the total, cannot be equal to I times omega. Well, this is not a symmetric case. Well, this is in fact why it fails. Now we can still test one thing though. Let's see, what is the direction? Let's call this axis our z-axis, and this is our angle theta. What is the z component of L? The total angular moment. This angle is theta. This angle is theta. So the z component is L total times sine of theta. Or twice L sine theta. What is the magnitude of L? You say this is L. So let's just call this distance d. So for each one of these L's, the magnitude of this vector is d. The linear momentum has magnitude m times omega times d sine theta. Remember, this object is rotating around this point with angular velocity omega. Its distance from this point is d sine theta. It is d sine theta, so it's omega times r is the speed of my object, m times the speed is the linear momentum of my object. So d is the magnitude of this one times m omega d sine theta is the magnitude of the linear momentum. And the angle between the two is 90 degrees, sine of 90 is just 1. So this is L. This is the total, this is L. And then we have another sine theta. Well, this is equal to twice omega. Or let me write it in this form. M twice m d times sine theta squared times omega. Now d sine theta is the distance of this mass from the rotation axis. So its mass multiplied by its distance from the rotation axis squared from this one, plus the mass of this object times the distance of this object from the rotation axis squared. They're just the same, so that's why I have this factor 2. So this is nothing but the moment of inertia. So you see the z component, which is in fact the component in the omega direction, is always moment of inertia for rotations around z times w. So Lz is always equal to I times W. So for such non-symmetric objects, L is not equal to IW necessarily. They are not equal vectorially. Well, in our case, we will be always dealing with spheres or rings, which are always symmetrical objects. For symmetrical objects, this holds all the time. The angular momentum is always in the direction of the angular velocity. But not necessarily for objects that are not so much symmetrical, like this one. It doesn't hold. For example, for this object, if you rotate it around this axis, angular momentum will be in the direction of angular velocity. If you rotate it around this axis, angular momentum will be always in the direction of the angular velocity. If you rotate it around this axis again, angular momentum will be always in the direction of the angular velocity. But if you rotate it through such a weird axis, the angular momentum will not be in the direction of the angular velocity. This is just to keep in mind. So if you apply these concepts, the results that we derive in certain situations, and you obtain some weird results, it might be because the angular momentum might not be in the direction of the angular velocity all the time. For those who watched the movie at the beginning, you see the object seems to be constantly changing its orientation. So the angular velocity vector seems to be constantly shifting. But the angular momentum of that object is conserved because there is no torque acting on it. If there is no torque, there's no change in the angular momentum. So for that object, for example, the angular momentum is not in the direction of the angular velocity. But in the simple cases that we will consider, it will always be. Now, any questions before you go for a break? Okay, see you after 10 minutes.